In this video, we're going to go over what the limit definition of the derivative is, why it makes sense, and how you can use it to find derivatives. Let's jump in. So let's start by first understanding the basic idea of what a derivative even is. We need the derivative to extend the concept of the slope of a line to functions that are not straight lines but are curves instead. Now, the problem that you have with any normal function, like y equals x squared in this example, is that it doesn't really make sense to say that it has a slope because it's not a straight line. However, the derivative allows us to salvage this idea by assigning a certain slope at each point rather than a certain slope for the entire graph. The question is, though, how do we do that? How do we actually tell which slope we should assign at each point? Basically, the idea is that if we zoom in really, really close, any curve is going to start looking more and more like a straight line. And then we can just take the slope of that straight line and say that's the slope at that point, or that's the derivative at that point. So, for example, around the point 0, 0, you can see what happens if I zoom in a lot. So let's zoom in. Here we're zoomed in about 10 times. Here we're about 100 times. Here we're zoomed in about 1,000 times, 10,000 times. Basically, we zoom in a lot. And again, what is a lot? 100 times, 1,000 times, 10,000 times, whatever, however much it takes. If you zoom in far enough, as long as a function is differentiable, and we'll cover exactly what that means later, basically, as long as you can take the derivative of the function, this will happen. And basically, you can see here that this line, when I zoom in this far, literally looks like the function y equals 0. In fact, if I told you that you were looking at y equals 0, you would probably believe me, because that's what it actually looks like. So what's the slope of a line y equals 0? Well, 0. It's just horizontal. So we would say that it makes sense to say that the derivative or the slope is 0 at that point. Now let's zoom back out and maybe look at another point. So remember that it's still the same function we were dealing with at the beginning. All we did was change our perspective. We just zoomed in a bunch. Now, if I go up to, say, another point, let's say maybe around 1, now I'm going to do the same thing, just zoom in 1,000 times or 1,000,000 times, however long it takes, but I'm going to zoom in around 1 now, around x equals 1. And then if I do that, so here we're zoomed in about 1,000 times at this point. Now the question is, what is the slope here? Hopefully you can tell by looking at it. You can kind of look at the squares here in Desmos. Again, there's like smaller squares inside of the larger squares, but whichever one you want to look at. If you look at this, doesn't it make sense that we're going over 1 square and we're going up 2 squares? So the rise is 2 and the run is 1. Rise over run is slope, 2 over 1. So the slope is 2 here, basically, is what we're saying. By the way, you could also have done this with the smaller squares here. The same logic would work there. Everything's proportional. So there you go. Apparently, what we're seeing is that on the graph of y equals x squared, it looks like when we zoom in around the point around the point 1, 1, the slope is 2. So keep that in mind. That's what we're noticing. Now, I'll zoom back out. Remember, we're not changing anything about the original function. This is still y equals x squared at each point. All we're doing is zooming in around different values. So that's good. Now, if I zoom out a little bit more, and let's change this to 2. So if I change that to 2, we can do the same thing. Again, same curve. We're just zooming in at a different spot. So now let me zoom in here. Zoom in. Zoomed in about 1,000 times right now. And let's ask ourselves, what is the slope? So, and actually, probably look better like this. So if you're looking at the larger squares, we're going to the right 1, and we're going up 1, 2, 3, 4. So rise is 4, run is 1, rise over run 4 equals 4 over 1. So the slope is 4. So apparently, on this curve at x equals 2, it makes sense to say that the slope is 4. So what we just saw is that this curve, f of x equals x squared, at the point 0, 0 has a slope of 0. At the point 1, 1, if you zoom in far enough, has a slope of 2. And at the point 2, 4, if you zoom in far enough, has a slope of 4. Obviously, we can't do this for every single point. We can't just sit here all day zooming in around all the points because there's an infinite number of points that we could have plugged in. So what we need, ideally, is a more efficient way to do this. But how can we do that? That's the question we're going to try to answer. So here's how. Remember, we know from algebra how to take the slope between 2 points. We basically just do the change in y divided by the change in x, or the rise over run. What we need to do now is zoom in on the 2 points we're taking the slope between as they get really, really close. And the best way to do that is with a limit. So what we've set up here, hopefully you can tell, is that we're specifically going to start off at one value of x. And again, we're leaving things general intentionally because we're trying to find an equation that works for all values of x, not just certain values. So in this case, it looks like we're starting off at x equals 2. So if that's x equals 2, basically the idea is that to find the other point, you could just go to the right by delta x. And you can see that's what we're doing here. So the x coordinate of this point would be whatever our x value is. In this case, it's 2, but it could be anything. And then right here, the coordinate of this point would be x plus delta x. And delta x is the gap between. So hopefully that makes sense. And if you know the x coordinate of this point, then you can find the y coordinate on the actual curve. You just plug x plus delta x in to the original function. So hopefully it makes sense that this point right here is x comma f of x in terms of its x and y coordinates. And this one is x plus delta x comma f of x plus delta x. We're intentionally leaving things vague so that we can work with these. And now that we have this set up, the basic idea is that we can calculate the slope between these 2 points like this. It's just going to be delta y over delta x, which is also rise over run, if you want to think of it like that. Now, that will calculate the slope between these 2 points, but remember, we don't just want to calculate the slope between 2 points. The whole goal here is to pull the points really close together to mimic the zooming in motion that we had before. So the way we're going to do that cleverly is by taking the limit as delta x goes to 0. And hopefully that makes sense. This value, delta x, as this goes to 0, this is literally going to force the points. This is going to force the point on the right closer and closer to the point on the left. And then as long as it's not literally the same point, we'll be able to take the slope, or we'll be able to calculate the slope at that point. And that is how we're going to simulate zooming in. Now, ideally, this is sort of a problem to calculate. What we would really like to do is express everything through delta x, because that's how we know how to evaluate limits. So ideally, what we would like to do is express delta y in terms of delta x. How can we do that? Well, if you think about what delta y is, it's really just this first y coordinate minus the second. Or in other words, it's f of x plus delta x, which is the y coordinate at this point, minus f of x, which is the y coordinate at that point. It's really just y1 or y2 minus y1. If you remember from algebra, it's just that y2 happens. We're just expressing it differently so that it is as a function of delta x. That's all. So hopefully it makes sense that we can rewrite this thing as f of x plus delta x minus f of x. That's really just delta y still, all over delta x. So there we go. And this expression here that we just came up with, this is what the derivative is at f of x. So this whole thing, if you want to think of it like this, is literally equal to f prime at a certain value of x, the derivative of f at a certain value of x. I should also mention one other thing before we move on. In most textbooks, you actually won't see it expressed exactly like this. You actually see it like this, most likely. You'll see it as limit as h goes to 0 rather than delta x. And then basically you're just replacing delta x with h everywhere. That's how you'll typically see it in textbooks. Now, this is not anything different. It's literally the same thing. Again, it doesn't really matter what you call your limiting variable. The reason that they decided to call it h is because back in the old days, students kept getting confused between x and delta x. They thought that they were the same values. They're not. They're completely separate values. X is like the input to the function for your derivative. It's the value you're trying to find the derivative or the slope at. Delta x is kind of a means to an end that we set up. We just set it up as a limiting variable that we intend to let go to 0 to basically force the zooming in. So it's basically, it's not used as an output, but just a means to an end. So these are two separate variables. They just changed delta x to h so that it would be a lot clearer to students that they're separate variables. But the h here fundamentally, geometrically, represents the change in the x coordinate. So it's still the same thing, if that makes sense. So if we try this idea and we actually take the limit visually as delta x goes to 0, or h goes to 0 in this case, you can see that the secant line between two separate points starts looking a lot more like the tangent line at a single point. And again, the idea is we're taking the limit as h goes to 0. We never let it actually hit 0. So they're always going to be a little bit off, but if you get really, really close, they'll be so close that they're essentially indistinguishable. And that is how it actually makes sense to take the derivative or the slope at a specific point. So that's what the limit definition of the derivative is and why it works. Now the question is, how do we actually use it? So let's use this new limit definition of the derivative that we just came up with to find the actual derivative of the function that we started with at the beginning, f of x equals x squared. If we just blindly plug this into the definition, think about what we'll get. We'll get f prime is equal to the limit as h approaches 0 of f of x plus h. The only thing we have to do differently here is replace f with what it actually is. So hopefully it makes sense that if this is f of x, they're telling us that that's x squared. Well, f of x plus h just means wherever you used to have x, put parentheses around it and replace it with x plus h. So you're just plugging in a separate input than x. It's just that that input happens to be represented with variables, which makes it a little bit more abstract, but it's fundamentally that's all we're doing. So this is going to be, hopefully it's clear, x plus h squared. Again, if the function was x cubed, it would be x plus h cubed. If the function was square root of x, it would be the square root of x plus h. Just wherever you see x normally, replace it with parentheses x plus h, and then that will be evaluating the function at x plus h rather than x. And then here, we're going to subtract f of x, which is just x squared, all over h. So there you go. Now, this is fundamentally a limit, and we can solve limits. We know how to do that. So if we solve this limit, we will get the derivative of this function. So now let's actually do that. The first thing that you want to do here, and again, depending on the function, different functions will have different methods of solving them or finding their actual derivatives through the limit definition. For this one in particular, whenever you're dealing with polynomials, the first step is always to expand things algebraically as much as you can. So if I do that, hopefully it makes sense that I would get x squared. If I just literally FOIL this out, I'll get x squared plus 2xh plus h squared. So that's what that becomes. And then minus x squared. So this right here is this expanded out. And hopefully that's clear. So then we have this. And now the next question is, where do we go from here? Well, if you're simplifying, hopefully it's clear that x squared and negative x squared actually cancel out. And this should happen basically every time you do the derivative. You should expect that to happen. So that after we do that, we're going to be left with 2xh plus h squared over h. Now again, the problem with this limit is that if we plug in h equals 0 here, we'll still get 0 over 0. So we're not quite done with that yet. However, hopefully it's clear that you can divide the numerator and denominator by one h. And if you do that, this h is going to go away, that h is going to go away, and will be one of these h's is going to go away. So we'll be left with 2x plus h. And then the limit as h goes to 0. Now we actually have solved our division by 0 problem. We'll no longer have an h in the denominator if we just plug in h equals 0. So now you can just plug in h equals 0, and then this h will go away. So long story short, what we just found is that the final answer here, the derivative of f, in this case, is equal to 2x. So that is the derivative of x squared. So this function is the derivative, and it tells us the slope of the original curve at every single x value. That's kind of the goal of what we were doing. And remember, at the beginning of this video, we actually kind of found those out through common sense. Basically, we just zoomed in to this actual curve, y equals x squared, or f of x equals x squared, around certain points. So we went around 0, 0, and we got a slope of 1. We went around 1, 1, and actually we got a slope of 2, not 1. And then we went around the point 2, 4, and we got a slope of 4. So because we zoomed in around each of these points and confirmed that these are the slopes, this is what we found. But I guess there's a lot of points that we didn't zoom in around. And you remember, it was not reasonable. You can't just zoom in around every point. There's an infinite number of points. So this function actually does that job for us as a function of x. So basically, if we plug in any x value here, so for example, if we plug in 0, Well, if you plug 0 into 2 times x, you get 2 times 0 or 0. So you can see that, yeah, this formula actually does tell us the right slope at that point. If we plug in 1, what would happen if you plug x equals 1 into this derivative function? You get f prime of 1 equals 2 times 1, which is 2, which is the slope that we saw. What would happen if you plug in this x value, x equals 2, to this function? You would get 2 times 2, which is 4, which is the slope that we saw. And in general, if you plug any x value into your derivative function, in this case, you're going to get 2 times that x value. So this is how you can figure out the slope of all the other points. So this is actually extremely powerful, this derivative. It doesn't tell us just the slope at one point. It encapsulates that idea of zooming in and looking at the slope that we did from the very beginning, but it does it for every single point in the domain, all infinitely many of them. And it's surprising that we can get all that information from just one function. So it's very powerful. So there you go. Hopefully that all makes sense. This is the limit definition of the derivative. That's how we use it. If you have any questions, feel free to leave them in the comments. Otherwise, I'll catch you next time. See you.